Oh.
And then
next Wednesday?
I
Not
add
two
5
Wednesdays.
11s plus 6 13s, and then 8 11 24.
Next one.
Like I'm just adding the numerator and
Two
adding
next
the
Wednesdays, or no,
denominators.
one.
Oh, right, okay, so
It's
it's
2
not-
Wednesdays.
It's not actually
So
adding
like,
the
yeah,
front.
Wednesday
so you
after
literally
next.
just have to add these
Yeah.
two, like add the numerator and denominator, you get
Mhm.
1/3. 1/3 plus 1/2, 2/5.
Mhm.
You just keep adding the numerators and denominators until you get like what you want, and it
So
like,
you
should
get
work
it.
out. And also send you pictures.
Good.
That Wednesday,
Yeah.
what day was
It
that?
took me forever because
That's
it was an
10-2.
example in
Oh,
class.
Wednesday.
Yeah.
But the example was with
Fourth.
the numerator is bigger than the denominator.
Oh,
So then
it's-
you always started off with like 1 or like 2 or something.
Oh,
So you start off with
yeah.
whole numbers.
And all of them were.
No, the week after.
No, okay.
Right, the week after, yeah. So homework 4 is due this Wednesday.
Oh, okay.
It's kind of just an outline.
Write down the product of Wait, yeah, for number 5 though, what does it mean when it says like write down the product for A1, A2, A3, A4? So you multiply them out associated to the 1 arrow to the next one.
I'm still talking about your drawings.
No, this is different.
I think it's saying like, you gotta give the convergence is what I did for associated here. Right?
So like P over Q.
So like you like the first two, and then create black. So, honestly, beats me.
Okay, I guess we're ready. Go. So today we're talking about maximum likelihood for continuous random variables. A new more example, dealing with the likelihood, multiplying the densities together, and things. And then we'll see a couple of different numerical techniques come in as possible ways of handling it. Next week we'll consider estimation, something called method of moments, or MOM, and some properties in homework 4 will be due. On this, either that Wednesday or Friday, I'll hand out some information about the first exam, right? First exam, we cover the first 4 homeworks. And the material through probably about chapter 6.2, right? Maybe 6.1, right? That we would have had exercises on and talked about a little bit more. And Monday will be review, right? So there'll be some practice problems, we can go over some of those, we can ask questions, and then just the in-class exam, right? And we'll say something about how that will be done, because a lot of the things that we've done on the homeworks have been computing based. So I'll probably give you some output from computing, right? You won't be asked to give me the R code for this and this and this. That's something you can figure out, from the computer, but that's not so interesting. It'll be more the ideas of what's going on, and with the output, what do you do with it? It might be describing some kind of pseudocode, like we described the little algorithms for doing things. You do this step, this step, this step. You do it a whole bunch of times, and so it might be a little bit of that. Yep, and then after the exam, we'll talk about the exam if I can get it graded quickly, and then to kind of finish up with some properties. There's one important thing called Fisher information that we definitely need to do. So we'll do a little bit here and a little bit down there. But that's kind of the forecast schedule for the next couple of weeks. Yes.
So there's no homework on the weekend?
There's no homework that week.
Okay.
Yeah. No, it's focused on review and doing this, getting ready for the exam. The homework after that might return to have some questions on the properties that we wouldn't look at yet in a homework. Okay, so maximum likelihood here for continuous random variables. So X is going to be a random variable. And then its outcome space is continuous. So it might be the whole real line, it might be the positive real line, maybe including 0 as an outcome, maybe not. Or it might be an interval, so 0 to 1, some random variables have outcomes that are 0 to 1, but they could be other arbitrary things. There's an angular distribution that goes -1 to 1, so there's different varieties. But some continuous intervals, so you might get any particular point and not just certain integers. Theta, in general, is a parameter, and that's often the goal. We often want to know that parameter, and it shows up in a probability model. So f of of x a density function given x. I might slip and write it as f of x given theta, but I mean the same thing. This f is a probability density function. And so at 2 points, x1 and x2, where the density is higher, there's a greater chance of seeing an observation. So like the normal bell-shaped curve, it says what are the chances of seeing probabilities in an interval. And so then we're going to get data, x1, x2, up to xn. And we're going to assume that they're independent observations. Likelihood approaches and our other estimation approaches work just fine if they're not independent, but then you need a different probability model, like a time series model or a longitudinal measurement model, to account for that correlation over time. Right? And so then once you get these data, our question is, what is the parameter theta that's governing the probabilities? If we understand that, we should understand chances, averages, standard deviations, and know a whole lot. And we're going to create an estimator. We call it theta hat to just correspond to that theta up there. And you might say it's a function of our data. So it might be written kind of theta hat of x1, x2, x3. So whatever our data comes in, it's going to give us a formula or a calculation procedure to get an estimate of theta. That's the big picture. Right? And we're going to do it particularly with these ones that the outcome space, the x's, have continuous possibilities. So let's look at an example. Right? So an exponential random variable has a parameter, we'll call it lambda. So instead of theta, we're going to use lambda. We're going to change the Greek letter corresponding to whatever the application is and what's kind of typical in terms of that one. So in this case, our variables values are greater than 0. The density function, f of x, is going to be a downward sloping function. It's 0 below that technically, but it's like this. So there's a great probability of having things that are close to 0. Right? And the exact form of it, f of x, the parameter lambda, is lambda e to the negative lambda x. And this lambda parameter has a parameter space that's greater than 0. So in particular, this model tells us a few things. All right, the probability that a random variable, that we see something less than or equal to some little value, say here's a little value. Right? If you do the integral from 0 up to that point, it turns out to be 1 minus e to the negative lambda x. Right? And the probability that you're greater than that ends up to be e to the negative lambda x. So if you want to know what's the chances you have something happens before this amount of time or in this interval happens, it's that, or the chance that it actually gets bigger. So knowing that lambda will give us critical probabilities. That would help describe what's going on. And in fact, the expectation of x, this is average or expectation in a probability sense, is 1 over lambda. So the bigger lambda is, the more concentrated this thing is towards 0. And the smaller lambda is, the longer the tail, and the more likely you are to have to wait a long time until you get an observation. Right? So we're going to take n observations. Each one's going to have this density. Right? And we want to combine the likelihood, the probabilities from each of those to get a likelihood, and then maximize that likelihood. So we got x1, x2, up to xn, the joint density of all the x's, meaning the density of x1, x2, up to xn, for that lambda, because of the independence, is a product. And each one of these, so there's a product I going from 1 to n of a lambda, e to the negative lambda xi. So that's the joint density of all the observations. Probability of first one, probability of second one, really the density of the first one times the density of the second one, and so on. And then we can simplify that, right? And so a question was asked, you know, when do you add, when do you raise to a power? And here's lambda, right? So there's lambda in the first one, lambda in the second one. You know, if we had, if n equals 3, it would be lambda e to the negative lambda x1 times lambda e to the negative lambda x2 times lambda e to the negative lambda x3, right? And we want to simplify that. And we get lambda cubed, right? And then, because it's e to that power, all those powers, those exponents get added together, right? So there's a e to the negative lambda, and then up here would be x1 plus x2 plus x3. Right? So depending on the exact mathematical expression, you either raise it to the n power or you add it up. And this is common, right? That it's not something that you've done a lot of for a few years, some of you, in terms of manipulating these expressions. So, you know, do it carefully, ask questions if it comes up, because in my experience, it affects a lot of students. Just because it's, you know, you might be doing higher level math courses, but doing these mechanics of this kind of type of thing, right, does. So this answer, simplifying that, there's lambda to the n, oops. Lambda to the n, and then the exponents, negative lambda, you can do the sum.
And since it has the sum, you don't have to like have the...
You don't need another n,
Okay.
nope, right? Because it just has the x1, x2, x3 that get added up here. The lambda, if you want to think about it, could be lambda to the first each time. And so it just adds up 1, 2, 3 to get up there. Right? So this is what we call the likelihood for lambda. And you could put, it depends on the data x, given the data x, but I'm just going to write it like that. So we want to maximize that. What value of lambda makes those joint probabilities multiplied together as big as possible? That kind of has the interpretation of the lambda that would be make the data have the highest density, right? Most likely. Right? So we'll take derivatives. I mean, you can take derivatives, or you can just take log. So the likelihood is the lambda to the n e to the negative lambda times the sum of the xi's. I'm going to write a little script L here, meaning the log of the likelihood. So we want to take the log of that whole thing, right? Lambda n e to the negative lambda sum of xi's. And so it's log of lambda to the n plus the log of e to the negative lambda sum of xi's. Logs of a product splits into the sum of the logs. And then the log of something to a power becomes n times the log of that. And the log, log here for us is always going to be, unless we really have a base 10 application, it's really going to be natural log. So these two things are inverses of each other. So it's just negative lambda sum of xi. And we're going to take the derivative of that with respect to lambda. Lambda is the unknown, so we're looking at where is lambda. So we'll take a d log of lambda, d lambda. So the derivative of a log is 1 over that value. And this is lambda times a number, right? So lambdas, you just get the sum of the xi's there. And again, in calculus, you use dx or dy, so it looks a little bit different. Right? But if lambda is the the thing that you're looking at, how it changes. And it's just lambda times that, and there's no power, right? It's just, you just get the multiplier back. So it looks a little bit different than ordinary calculus, but it's the same idea. We set that equal to 0. So n over lambda equals the sum of xi. And so lambda 1 over that and equals n over the sum of xi, which is 1 over x bar. And we call that then lambda hat. That's our maximum likelihood estimator. So based on the likelihood, how do we estimate lambda? If it's exponential, it says to calculate the sample mean and take 1 over. Has a little bit of sense, right? The mean was 1 over lambda, so it's kind of nice that it says that it comes up with this. I mean, it might have said take 1 over every x and get the average of those, right? But it doesn't. It says to do this, right? And so that's how we get that estimator in that case. Right? After we talk about, so Wednesday, Friday next week, we'll talk about properties. This is a good estimator. What's nice about it, right? And so maximum likelihood estimators have large sample normal distributions. So they're normally distributed. They're efficient in a certain sense. And so there's a nice thing. So there's something called Fisher information we can use to estimate the variance of that. So we get a kind of a compact tool for getting a confidence interval for lambda out of this. But that takes a little bit more work to get to. But any questions about it? So today we're looking at a couple more examples. So let's say that the xi's are distributed as a normal random variable with some mean mu and some variance equal to 4. So that sigma, the standard deviation, is 2. So that would say that the data we have is centered somewhere here at some mu. And a normal usually has about plus or minus 2 standard deviations. Plus or minus a couple 2 from that is the bulk of this curve, right? So actually, so mu, since it's 2 plus 4, or mu minus 4, is a big chunk, almost a little bit more than 95% of that area. But the question is, where's mu? Right? So the normal density curve, f of x. Now normally there's 2 unknowns, but we're just going to deal with 1 unknown at this point. Right? Has a certain form. In general, it's 1 over sigma square root of 2 pi e to the negative x minus mu squared over 2 sigma squared. But if sigma is 2, this can be written as, I'm going to write it as 8 pi. Pull the 2 inside and make it a 4. And this one's e to the negative x minus mu squared over 8. Yes. I said something slightly different in my notes, but this is what it is. So, anyways, it'll work out for us. Right? If I want to, each I, right, there's a little subscript I that can be put on each of these things, right? So each point is sampled with that normal density. So now we get n observations, x1, x2, up to xn. And our likelihood for mu is going to be the product going from 1 to n of this density, which I'll write on the next page. This is the joint density of all n observations. Right? So it's probably best to write it on the next page just for space. But again, we take that density and multiply it together, and we'll figure out how to put it together. So the likelihood is a product I going from 1 to n is 1 over 8 pi square root. And there's a negative of xi minus mu squared over 8. So that's all a product in there, right? So kind of like the exponential one, we have just a number out here or something that doesn't have any x's in it.
You can pull it outside.
So you can pull it outside, but it's multiplied n times. So there is a 1 over square root of 8 pi to the n, right? Because there's n copies of that. There's one, x1 has one, x2 has one, x3 has one, right? So there's n copies all multiplied together, and it's that. But in this one, the first one has x1 minus mu squared over 8. The second one has x2 minus mu squared over 8, etc. And so those exponents add. And they're all negative. So we get a negative. And then there's a summation, I going from 1 up to n, of xi minus mu squared over 8. So that's all up there in the exponent. Now we want to maximize this. What value of mu maximizes this function? So what we can do, we call this the log likelihood. The log of this, we get n out front times the log of 1 over the square root of 8 pi. But 1 over can be, you can put the minus out there and just make it 8 pi. So you could write this as square root of 8 pi to the negative n. And so there's a negative n out there. You could do it either way. And then this, so that's one part. Right? And then log is the inverse of that one, so it's negative the sum of xi minus mu squared. And there's 1 over 8. It can be pulled out there. Right? So it's not 8 to the n, because the 8 was part of the thing we're adding together up here, right? If there was a separate e to the 8th, then there'd be e to the 1/8 to the n, but it's not. It's part of that. So all of that gets added together in there. So we're going to take a derivative of that and set it equal to 0. That maximizes the log likelihood. It gives us the same solution as if we had just done the calculus on that one, which is pretty messy. Right? I think once we'd taken the derivatives and regrouped terms, we would have to do a combining step anyway to figure it out. So if we take the derivative of this thing with respect to mu, well, mu's not over here at all, so that's just 0. And then we take the derivative of this thing. Well, the derivative of a sum, the derivative comes inside, so well, it's minus 1/8. Let me erase this so it's not a duplicate. It's a sum. The derivative of this thing is 2 times the xi minus mu. And then there's this. It's expressed as a negative. So there's another negative, so it becomes positive. You set all that thing equal to 0. Well, the 1/8 and the 2 as multipliers don't particularly matter. So you can put the 2/8 out front. The 2 can go out there. And so what we're really doing is seeing where is the sum of xi minus mu equal to 0. So it's a derivative step. So there's the combining step. Here we write down that, combine it, take logs. Right, so we get this one, and that's the sum of the exponents up there. Take the derivative, right? So that goes away, and the derivative of this thing ends up being that. So we're really interested in the sum of xi minus mu equals 0. So the sum of xi minus mu equals 0. You can split that one there. The sum of xi. This is n times mu, because it's mu and it's added up n times. Right? So the sum of xi equals n times mu, and mu equals the sum of xi over n, which is just x bar. And we call that mu hat our So the maximum likelihood estimator of the average in a normal sample is just the sample average. Now,
So the 2/8 don't matter.
the 2/8 thing doesn't matter in that, because you know, if you had 2/8 out here, you can multiply by each side by 4, and it'll cancel that, and it doesn't change the zeros over there. So that's yeah, that multiplier out there doesn't change the sum. Right? So that's good. I mean, that's convenient. It's the average. It's symmetric. You know, so this would be our kind of common sense one, and it ends up being that. Right? The exponential with 1 over x bar, right, is kind of common sense too, but not as obvious. But that's what it comes out of this. Let's do one more normal, right? Let's say that the xi's are independent random variables, and they're normal centered at a mean of, say, 5 with some variance sigma squared. So this model would say that here's 5, you know it's here, but you don't know how spread out it is. Somehow your process has been engineered to have that 5 average, but you know, you're building tubes that allow a certain flow of water going through, and they're engineered to be 5, and you believe that it's on average, but there's a little bit of variability in the process. How much plastic gets in there, how much gets molded and cut off exactly. So it's 5 plus or minus. And how much is it? Well, you might be willing to keep it as 5 if you believe the engineering, but we might want to estimate that. Right? So now the density for Fi, we could write a sigma squared here, or sigma. Right? And there's 1 over sigma square root of 2 pi, e to the negative, and up here is xi minus 5 squared, that's number 5, over 2 sigma squared. So now the parameter shows up twice, that's okay. Let's have to deal with that. So we're going to get data in measurements of our tube. Take the product, x1, x2, up to all these is the product of these. So if each of these things are in there, some things just have sigma and a constant with no x's, right? So those things are going to get raised to the n power when we do the multiplication. Otherwise, you're going to get a summation because x is involved. Yes?
How do you get 2?
How does a 2 end up here? That's just part of the normal density equation. That's just the curve that Newton worked with, or something like it. But it's the modern version of it. It's actually kind of an incredible thing, right? Because square roots of pi, and pi, square root, and e, you get 2 transcendental functions in this fundamental equation for things like, who would have guessed? Right? Anyway, so n times, right, so I'll do it the direct way, 2 pi, right, and there's an n here, there's n copies of that, 1 for each xi, and there's an e to the negative, and there's a sum of 1 to 2 of xi minus 5 squared, and 2 sigma squared in there for the normal densities. All right, so we take the log of that thing, right? So the earlier question about when do you get ends, when do you combine, is directly relevant for all of these, right? And it'll be useful in the homework to keep track of. So if you're going through this and have done some and are just a little unsure if you've done it right, if you want to come to office hours on Monday or Tuesday for a quick check, that's fine. Or if you go through it and get something that kind of looks like it's going funny or has a funny number in it, you know, you could send an email saying, I got this, could that be right? And I'll try to, give an answer before, pretty quickly to that. So we take the log, that's the likelihood. So the what I've been calling L of sigma squared is the log of the Ly. Right? So the log of that is there's a negative n, there's a log of sigma square root of 2 pi is in there. Right? It could be n and then 1 over that, but things that are 1 over are also a negative there once we get the log. And then there's a negative sum of xi minus 5 squared over 2 sigma squared. And this might be split up to negative n log sigma, and it's a log of a product, right? So then you'd have negative n log square root of 2 pi. The log of that is the log of the first one plus the log of the second one, but there's this negative n that applies to both, so it's in there. And then this thing, over 2 sigma squared. So we'll take the derivative. Now this one is right, is it sigma or sigma squared? And let's just, it works either way. Let's do d sigma. There's another thing about likelihood equations is that there's a translation invariance. You can do likelihood for sigma or sigma squared or sigma cubed, and the maximum likelihood estimate of sigma squared is going to be the one for sigma squared. Right, so there's a translation, or there's an invariance that works there. So you can do it, the derivatives with either version. So let's do this one, right, because that's there. So this one is just negative n over sigma. This one doesn't have a sigma, so that's gone. If you kept it together, you would get 1 over sigma squared root of 2 pi, and then you multiply by square root of 2 pi over top, and they would have canceled, and you'd be in the same place. This one, right, there's a sum of xi minus 5 squared over 2. Now the sigma squared is sigma 1 over sigma squared is sigma to the negative 2. Right? So we end up with sigma cubed down here, right? So that goes up, and then you get a negative 3 out front. So negative 3, so that becomes positive. Side, right? So that's the mechanics of dividing by taking a derivative of 1 over something squared. Right? It becomes 1 over that thing cubed, and you get the negative. We switch screens. And you get the negative 3 out front. But there was a negative before, so now it's positive. Right? So set that equal to 0. Right?
Wait, why do you get the 3 out front? Do you not get a 2 out front? Or-
You don't get it. Maybe do you get a negative 2? Yes, you
I
do.
could be wrong.
I'm thinking about integrals, not derivatives. But so you get a 2. Sorry about that. Yeah.
Why do you have?
Right.
Oh, there it
So
is.
those will cancel.
Yeah.
Right. Yeah. Right. So let's multiply through by sigma cubed. Yes.
Is the 2 sigma cubed in the summation, or is it dividing by the whole 2 summation?
You could put it either place.
Okay.
Because it's a constant, it will go through the summation
Okay.
and multiply every term. But you can also pull it out.
Okay.
Let's multiply by sigma cubed, so we get negative n sigma squared plus. And now because it's a 2, those cancel, which is nice. And that's gone, so it's the sum of the xi minus 5 squared, and that equals 0. Right? So what we did there is multiply by sigma cubed. We get that. And so if we put this thing on the other side, n sigma squared, that would go over here, is the sum of the xi minus 5 squared. And so sigma squared is estimated as this measure of variability, right, divided by n. And that's what you can call that the maximum likelihood for sigma, or if you take the square root of that, so sigma hat, oops, sensitive down there. square root of that whole thing, right? Take the square root of this whole thing, that would be sigma, getting rid of the square. And so it's the square root of that expression. Okay. Sample variance, you take xi minus x bar squared, divided by n minus 1, so that's the usual sample statistic. And so this says don't use the usual sample statistic. If you know that the mean is 5, 5 is going to go there, not x bar. And it says to divide by n, the number of observations instead of n minus 1, so it's a little bit different. But any questions? So let's see, 205. So, whether to do a multivariate one. So you can't do both things for normals. You can't do both at once. So if xi is normal with mean mu and variance sigma squared, right? There really are two parameters. And the book has a little bit of detail of this. This is in their section on multivariate, on multiple parameters, right? It turns out that the density for x1, x2, up to xn, with both of these parameters is, there's a square root of sigma 2 pi. Now I'm just jumping to all in observations instead of multiplying it together. The density's in the book, and you can see kind of step by step. But it ends up being that, and then there's an e to the negative 1 over 2 sigma squared, and a sum of xi minus mu squared. So both parameters show up in there. And now, maximum likelihood is choose both parameters simultaneously to make the data most likely. Right? So in a normal case, you're choosing the center, right? And you're choosing the spread, right, to match your data optimally. And if you change the, right, so here's the normal curve. There's some value of mu, and then something like mu plus 2 sigma, or mu minus 2 sigma over here. And if you have some data points here, right, what you're looking at, the individual densities are these heights up to this curve. And you multiply all those together, or add together their logs, right? And you want to choose the mean and the spread. You can spread it wider or narrower, and you can shift it so that those points are as high as possible when all multiplied together, right? So you don't want any of them to be too small if you can avoid it, and you want to get a bunch of them that are as tall as they can be, right? And so maximum likelihood tries to center over the data in response to the data. And so that's the likelihood, so we want to maximize that thing. Right? So we take the logs of it to make it a little easier to differentiate. So that's the likelihood for mu and sigma, or mu and sigma squared, either way. We're going to take the log of that. The log of this one, mu and sigma. And so negative n is a log of 2 pi sigma. There's a square root of 2 pi there on that one. Right? And then a minus negative 1 over 2 sigma squared, a sum of xi minus mu squared. And so using calculus to maximize this uses partial derivatives. Right? You have to take in account both mu and sigma. So that's, if you've had Math 130 or Math 150, doing partial derivatives is a step beyond that. But we've already done a little bit of a step because we've gone for not differentiating x and y to differentiating mu or lambda or something like that. And so in this case, what it basically means is we do them separately. Right? And instead of writing d's, you write partials to indicate a derivative. So if you take a derivative with respect to mu, you pretend sigma is a number, a constant. Just like before, we called it 4, or 2 for sigma, or 4 for sigma squared. Right? Just imagine it's a number, and take a derivative of what's left. Right? Well, mu's not in here, so that doesn't change as mu changes. So it's 0. Right? This one, mu's in there. The negative 1 over 2 sigma squared is a constant. We can do the derivative with respect to mu inside. So there's a 2 times xi minus mu here. And then there's a negative also, so that becomes plus. So this equation, in this particular case, we can actually solve for just the mu parameter. Right? It's kind of a sum of the key thing, the 2 can be pulled out, so we need the sum of xi minus mu equal to 0. And just like before, mu hat is going to be our sample average x bar. That one works out just like it did when it was just mu, when we pretended sigma was known. That's the maximum likelihood estimate still for the average. So we get that one, right? And now we take a derivative with respect to sigma. We'll use this as the MLE for mu, and then get that one. So there's the second partial with respect to sigma. Well, if I do my thing of splitting that out to 2 pieces, there's negative n over sigma. The square root of pi part either cancels out or you would get rid of it. Right? And then there's a negative, right? There's negative 2, so it's negative 2 over that to negative 3. So I can get this down here. That seems like enough space, like the barrier. So it was plus 1 over sigma cubed, the sum of xi minus mu squared.
And mu is.
Mu is going to be the x bar.
Okay.
Right? But just taking the symbols, it's still mu. Right? And if we multiply by sigma cubed on these things, then we get negative n sigma squared plus the sum of the xi minus mu squared equals 0. And so we end up with a solution that sigma squared is the sum of the xi minus mu squared over n. And what we're going to do is put the x bar in there for that one. And that's going to be the sigma squared MLE. So in the previous one, when we said we knew that mu was 5, we put 5 in there. But in this case, with both at the same time, we're going to get the average to use for mu, and we're going to do that one. This is the letter mu, the Greek letter mu here. So you can do 2 at once. Right? They don't always work out so nicely as the normal. But you have the normal, you estimate the mean, and then the standard deviation. The ordinary, s squared, would have been minus 1. So the maximum likelihood is a little bit different than that. That's okay. It's just, we'll talk about the differences. For larger sample sizes, n or n minus 1 doesn't make a little bit that much difference. This estimate, a little hat on there if you want, is a little bit less because you're dividing by n instead of n minus 1, but that's just what the theory says to do. Let's do a new one. We'll just keep going, getting the practice. Now, a gamma random variable, I'll write it like 3 with lambda. This density equals lambda cubed over gamma of 3 xi squared e to the negative lambda xi. And gamma random variables are positive random variables. This is the density function here. This gamma of 3 value is actually 2. If you look at those random, oh, I wanted to mention appendix C. There's an appendix C in the book, right, that has some common distributions, that has some means and variances, that has some moment generating functions, which we might use later, but it has some of these, so it would have, this would correspond to one of the terms there. I might have used a different letter than they use. I think they use R and lambda. Anyway.
Yeah, they use R.
Right. So the joint density for lambda, that will be our log likelihood, is the product of this thing over n times. Right? So you'll get a lambda to the 3n gamma of 3, which is 2. So I'll just make it 2. 2 to the n. Now inside here, there's a product. Every xi is raised to the squared power. So that's a little different. And there's an e to the negative lambda, the sum of xi. Now I've skipped, that's the picture here. I've skipped writing out the details and doing it so slowly. So I encourage you to check it out. Practice it if you agree how it combines. The key difference here is there's an xi. So there's x1 squared here, the next one multiplied on there has an x2 squared, and so that's x1, all of them product together.
And you know R3 equals 2 from based on like the appendix.
This is, yeah, just dealing with this. This is really from just that gamma function. So that would be kind of a probability thing where they talk about that. There's a couple other appendices, one that does more with probability, and so you could just leave it as gamma of 3. When we take the logs and differentiate, it doesn't involve lambda, so it's going to go away.
Yeah.
Anyway, but that's the numerical value, right? So the log of this thing, right, 3n log of lambda is a minus n log of 2. What happens to this thing? Right? Log of something squared, so you get 2. Yeah, the product turns into a sum, and then there's a log of xi's. That ends up there. And then the log of the e thing becomes minus lambda times the sum of xi's. Right? So if you differentiate that, with respect to lambda and set it equal to 0, you end up at lambda hat ends up being 3 over x bar. Right, so the 3 ends up being in there, 3n, and you get and the sum of the xi's are here. The sum of the xi's divided by 3 over the sum of the xi's is what you end up. It isn't working out very much like the exponential one in terms of getting 1 over x bar, but there's that 3 in there, so it gets incorporated this way. So I'll let you check that one, because after combining and logs and differentiation, it's kind of the same deal. So sometimes it looks like what you do expect, sometimes it's a little bit different. We want to look at least one example where you can't do it so explicitly, but you can still maximize it. So as an example, xi is gamma, random variable, the first coefficient is unknown, is alpha. So alpha is our parameter. But 5 is known, the second parameter. They have to do with mean and rate parameters and scales. So they have their meaning in terms of means and variances and things like that for the random variable. So in this case, the f of xi, and I'll just put lambda in there, is 5 over gamma of alpha. can't get rid of that. Right? Xi, can't replace it with a number because you don't know alpha, and it might not be an integer. That's the function. Right? That's the density. That's the picture that gives you the curve that shows you where the values are likely to be. So our likelihood for alpha, which is a product over the n independent density pieces, this thing all multiplied together n times, so we get a 5 to the n. There's gamma of alpha to the n. x1 to a power, x2 to power, all multiplied together. So you can do the product of these things, raise the alpha minus 1, and e to the negative 5, and you get the sums up here. When it gets complicated like this, I would suggest doing an x1 times an x2, and then seeing how you would combine it with just 2 terms. Right? That could help. Or then try it with 3 terms, right? So then that would give the pattern. Where do you do products? Where do you do ends? Where do you do sums? This has all 3. So we did the log of that thing. Now log, what we're calling this thing. Right? So there's n log 5 minus n log gamma function. There's a alpha minus 1 times the sum of the log of xi's. All of that then minus 5 times the sum of xi. And we'll differentiate that and set it equal to 0, but it's not going to be a very nice function to solve. So you take the derivative, and it's not something that you're going to easily set equal to 0, right? But we could, if you could solve it. This is the hard way to go about that, because it involves a gamma function and the derivative of the gamma function, which are things that are in R. You can evaluate them. But to solve that equation, it's difficult. So I like this example because we're going to do it a different way, right? We're going to do it computationally. We're going to use the computer for it, right? That instead of finding the exact maximum, we're going to use the computer to search across a lot of different values of alpha to find the one that's the best. So numerically, we're going to find something very close to the maximum. Right? So let's say gamma alpha is what we're interested in. Let's pretend that in reality, alpha is 4. The mean of the gamma would then be about 0.8, because it's the ratio of the 2 variables, actually. And then let's generate some data. Instead of random number C, let's generate 25 data points. And here's random gamma variables, 25 of them with the parameters 4 and 5. The average ends up being, the mean is 1.99. What do I got before? Oh well. 1.99. We'll use that. Right. And so what we would like to do is be able, what our goal is, right, is we have this likelihood function over here, which is the density of a gamma is all multiplied together. We would like to find the value of alpha that makes this as big as possible. So our strategy is to put in a value of alpha and evaluate it. Right? X are numbers, our data, right? 5 and n, we know it's 25. 5 is there. Put in gammas, alpha. Put a value of alpha, say 4.2, 4.1, 4.0. Right? And we can evaluate this to see how high that curve is. And if we do that at a lot of values of alpha, we'll get the likelihood function. Right? We will get L of alpha. Or if we do it on a log scale, we'll get this one. Right? And so that will show how high would the likelihood be for the value of alpha. We want to find the alpha that gets us as high as possible. So that's what we're doing, right? Through all this calculus and setting things, derivatives and stuff and combining terms, I mean, we're doing it, algebraically with calculus to get an exact solution when we can. But this one is messy because of that gamma function. And so where we're going, there it goes. So we're going to set up a grid called alpha grid. It's going to go from the number 0.1 up to 10, so alpha under a gamma can go anywhere positive. It's not restricted to be, it just has to be a positive number. So we're going to set up this grid. My alpha grid, if I look at it, is all these numbers by 2.10. Not terribly fine, not terribly precise, but it covers a long range. I'm going to make a log likelihood evaluation at each of those points, do a little loop. I'm going to go over all the length of my grid, and there's a d gamma function. Conveniently, I can get that gamma function, and I can do it on the log scale too, for a particular value of alpha. So the first one I'm going to do is 0.1, which is way far away from the truth. Probably not a very good choice. Right? But I'm going to evaluate all the densities there on the log scale and add them up. Right? And that's going to be the value of the log likelihood evaluated at that particular alpha. So let's see, run through all these calculations for me and I can plot it. So this is the log likelihood function. That's the little l of alpha, log L of alpha. This is the function, right? So the maximum is somewhere around 4 or 5, something like that. Right? And so what I've been doing with calculus is taking the derivative and setting it equal to 0, and then solving for that point. Right? But this one doesn't work out so well.
So you brute forced it.
Brute forced it, yeah. Well, mostly. I mean, the fact that they have a d gamma function on the log scale makes it nicer, but you could have some strange thing that's not, strange density that's not exactly in R. There are many that get used in engineering or other sciences, I think that would not be in there. Where does the maximum occur? A little which point has the maximum? The maximum occurs at 4.1. So for some reason my data is different than when I simulated it. It's possible, that it was the red line in there, that I ran it and then I changed something and I reran it again, so I ended up with numbers that didn't match my code. So 4.1, so I don't want to search between 4.1 and 4.2. I'm going to try to get this a little bit, 4.1 is not that precise. Right? So I'm going to do a new sequence of numbers between 4.1 and 4.3 that's as many points as I had before. Right? So I'm going to try to narrow in on that one point. So that's my new alpha grid. But then I'm going to run this loop again. Recalculate the likelihoods on that new thing and do a new plot. Oop, it's pretty close to 4.1. I better adjust my grid a little bit. Let's do 4.0 to 4.2. And then rerun all that and do a plot and then the maximum. The new maximum occurs at 4.11. 5125. I should correct it, 4.11 by 152. So that gives me more decimal places as to where that is. Say I want a little bit more, 4.11, so I'll do 4.11 up to 4.12, and I'll do 10,000 points between those two, right? That's give me a lot of precision. So I'll change my grid, and then I'll run the calculation again to calculate my log likelihood again. Oops. There we go. It's sensitive. I don't rerun. Okay, we'll make this bigger so I can grab it that easily. And so now it's very dense, and it tells me my maximum occurs down here at 4.116, basically. 5997, right? And so that's very precise in terms of that value of alpha. Right? Actually, we're doing it with a closed form solution. You carry along as many decimal places as the computer can handle, but this is pretty good. Right? The value we used for generation was 4, so we're pretty close. I mean, we're not going to get 4 because our sample is random. It implies that the mean 4.116 over 5 is 0.82. Whereas 4 over 5, our mean from the process that generated the data was 4. But we get pretty close to the mean implied by that. But our estimate of that one parameter is 4.5, right? So if we wanted to, we can plot that gamma density if we wanted to see, we'd see how it goes with mean and variance and stuff like that. So we're still trying to do the same thing. We're still trying to find the parameter that maximizes that. We've got to do a little bit more work to do it. So I think that's what we'll do for today. We'll probably start on Monday with an example or two that does other computing and looks at the method of moment. Right? Yeah.
Do you do like a similar process, or do you want to do one?
Yep, and then you can multiply them together.
Oh, and then you multiply it. Or what do you do with the 2?
So it'll be a 2 lambda there and a 2 lambda there.
Oh, okay. Okay.
Yeah.
Thank you.
Yeah, Heather.
Have a good one.
Have a good weekend.
Thank you.
Thank you.